Thanks for sticking around. One thing I didn't mention before is some people here may find this interesting. A big part of my life is traveling. I don't really live in one place. I'm a digital nomad, and I travel around and work from my laptop. I've been in Central and South America. I've been in Canada for 6 months. I was born in the US, and so I'm living this life, getting to meet so many people all around the world, pretty much, who are into Bitcoin. I've been to various meetups around the continents, and yeah, so if that's like something you're interested in, I can help you with that or answer some questions there. It's a really, really interesting way to live your life, and if it's something you're able to do, I would totally say do it. So yeah, just something I forgot to mention in the first talk. So, okay, now I want to dive into the technical side of Bitcoin. I want to answer some of the questions that I kind of left lingering before, talk about mining, talk about what does validating a transaction actually mean. Yeah, and you can keep me on track and make sure I'm not rambling too much, because this is really the stuff that I love to do. I'm a software engineer. I'm a technical person. This is what I do every day. So hope to share it with you. Hope you get something out of this. And really hope that you can download these tools online and use them and be a blockchain Bitcoin developer. Write software which creates transactions or creates smart contracts. I want to get to that at the end. Hopefully we'll have time. But it's totally doable. If you're a software developer, if you're an engineer, you can do that. And I hope to give you the tools right now where you can wrap your head around some of the stuff. Okay? Let me skip forward. Okay? Yeah, next one. Okay. So the way I want to structure this is I want to walk through what sending a transaction looks like. And we're going to talk about like the software, the miners, what addresses are, how we use cryptography to power Bitcoin, and then how those transactions are broadcasted through the network. And yeah, so you'll see the whole flow from beginning to end. Okay. Can you go to the next one? Yeah, and if for whatever reason you get nothing from this talk, I won't feel too bad, because I will have told you if you want to understand more, if this didn't make sense, really, really what you should do is go and read the original, what's called Satoshi white paper. This is the paper that I mentioned in the last talk. It's 9 pages. This is what started it all. And even though it's like PhD research level stuff, it was really new, it's the most readable piece of research I've ever seen. You only need high school math to really understand it. And it's really short. It's not like these 100-page research papers that are totally unreadable. So give it a look when you get home, and it'll be a good way to teach yourself too, if you want to learn more. So first off, this all starts with the developers. Satoshi, other well-known ones in Bitcoin are Greg Maxwell, Mark Friedenbach. There's really a community of over 500 of these developers contributing their time and to writing Bitcoin software. And there's hundreds of projects. My company is just one of them. There's both open sourced and closed source and everything in between. And they're in a bunch of different languages. So the main one is written in C++. There's also one written in JavaScript, Java, Go, .NET, whatever language you want. There's an implementation of the Bitcoin protocol probably in that language. Okay, so starting out sending a transaction. I want to get some coin and send it to Ramsey. So how is that going to work? Well, the first thing you need to do is you need to have coin to spend. So where does that coin come from? Someone sent it to you before, but then someone had to send it to them. Then you travel all the way back. Where did the original Bitcoin come from? The answer to that is the miners. So mining, you may have heard of it. There are miners all over the world running this computer algorithm, this computer program in order to mine. What they're doing is they're rolling a dice such that on average, it's not always, but on average, every 10 minutes, someone in the system who's mining finds a solution to this problem, this mathematical problem that involves rolling dice, and they get roughly $100,000. And they get paid because they put in time and money and effort in order to find this. By running these mining rigs, maintaining them, paying people to maintain them, cool them. They're putting in money, they get a reward in return. Yep. Okay. So they get money for doing that. That's where the original coins come from. Every 10 minutes, 12.5 Bitcoin are just injected into the system from thin air. But the other reason they mine is because they actually do something useful for the network. They secure the network. They take all of the transactions which are insecure, unconfirmed is another word for them, and they mine them, bundle them into a block, and present them to everyone in the system. And that's where Bitcoin gets its append-only nature, where you can't remove once it's been included. Once a block has been mined, it's very, very, very difficult to remove the block. Pretty much, yeah, no one does it. It's very difficult to remove the block and replace it with something else. So miners have two purposes. Just remember that. Gotta generate some form of currency, like injecting it into the system without a third party. There's a bunch of decentralized miners all over the world doing this. And I mentioned this before, by securing the network, really what they're doing is preventing what's called a double spend attack. So let's see how we can go through this. I'll just flip like this when I want you to go forward. So we have three folks, Alice, Bob, and Mallory. And Alice, can you go back one? Alice has a Bitcoin. I can't see it too well, but that yellow thing is 1 Bitcoin. And the double spend attack is where whenever you have a currency, like a fundamental property of it is that if you give the currency to one person, you cannot also give it to another person. So imagine we naively, we tried to make a digital currency, or we tried to take something like USD, like a bank currency, and make it into our own currency that we would use and be Bitcoin-like. Who is going to stop if I say I want to send a transaction here to pay my rent? Who's going to stop me from sending that same amount elsewhere? Because it's all computers, right? It's all zeros and ones. And the problem with zeros and ones is that they're infinitely copyable. And if bits are supposed to be the thing that is scarce and can only exist in one place, and you can copy it, what do you do? How do you solve that? So you can skip forward through that. So, yeah, keep going. So the way you solve it is by making people or creating a system where people are incentivized to do a ton of work, mining, ton of work, and get paid for it in return. And then everyone in the system agrees, all right, if this person can prove to me that they did a bunch of work, then I'll let them have this 12.5 Bitcoin. I won't be able to reverse these transactions that have been included in this mined block because I would need to do an equivalent amount of work to take out these transactions and put in some new ones. And it's just not worth my time. It'd just be burning money to try to replace this block. So it's really, really clever because it solves two problems at once: securing the network and generating coins. Mining does both of those at the same time. Two birds with one stone. So what does mining actually look like? I keep saying that it's rolling a die. Really what it is using something called a cryptographic hash function. So,
Alex,
yeah.
I have a question.
Yeah.
So You started by saying that if you want to create a transaction for me,
Yeah.
You should spend the money that you have already received from someone else.
Yeah.
So let's say that you have received it from Zacho, and Zacho received it from Mark, and Mark received it from David. But if we actually track back this transaction,
Yeah.
will it also lead to the transaction being generated by a miner?
Yes.
So
Yeah.
always all the UTXO of a transaction can be linked to a miner that generates this money.
Exactly.
Right?
Yep.
Okay.
Yep.
Awesome.
Yeah. Thanks. That's a good clarifying point. Like anytime you've ever spent any coin, it originated from a miner at some point. Maybe it was from a block mined 2 days ago. Maybe it was from a block mined 5 years ago. You could actually trace it through to see it, but they're all the same. The coins are all equal in their spendability. So going back to hash functions, you may have heard, if you're a software developer, you may have heard of a hash map, which is just a data structure where you have keys and values. And a cryptographic hash function is sort of similar to what's used in a hash map, except it has some extra properties about it that make it good to be used in a system like this. So the basic idea behind a cryptographic hash function is that it's a function, so it takes an argument, it takes some piece of data, and then it mangles it and flips it around and twists it and contorts it in all these ways and pops out a random number. And the random number is always the same length. It's 256 bits, which is like 1 followed by 80 zeros, roughly long. So, right, you have a function, put in data, pop out random value. And the other interesting thing about a cryptographic hash function is that, let's say I have some data and I run it through the function and then I have this, what's called a hash, the output value. If I were to take that hash and give it to you, you would not be able to tell what the original data that was put in. You would not be able to kind of reverse engineer. You wouldn't be able to backtrack and figure out what the original input data was. Another interesting thing about it is that, let's say I take some data and I hash it and I have an output value. If I go back and I take that data and I change 1 bit, just a single bit, even if the data is like kilobytes, megabytes of data, change 1 bit, feed it back in, the output, the random value, it's random. About half of the bits will be different. Even a little tweaking on the input data will result in a totally different output data. So this is why I called it earlier rolling a die, because you're like rolling the die is hashing some data, which I'll talk about what the data is. You're hashing some data and getting a random value. That's really what a dice is. A dice is just a random value that you can generate every time you roll. The thing with this die is that it's like has so many faces, the number is so large, it's really hard to describe. Imagine a die with 10 followed by 80 zeros, different faces. So you can't see it too well, but an example there is where I have the input data just 1, just a piece of data, and then I input the data 2, right, 1 bit difference, and it's a 256-bit string, totally different. And you can verify this yourself on your computer through the terminal, if you'd like. So this is what the actual function looks like. So SHA-256, SHA stands for Secure Hashing Algorithm. The 256 means the output is 256 bits. You run that twice on your block. So remember, a block is like the miner sitting there. It grabs transactions as they come in, puts it in this block, which is a blob of data, and then it uses this number called a nonce, which stands for a number you only use once. So it itself is also just a random value. And you take these numbers together, plop them together, put them through the hash function twice, and you get some random value put out. Okay? So you'll notice this value doesn't look very random. Why? Because it has all these zeros in the beginning. Going back to mining, every miner, like at this point, there's miners all over the world, and they're sitting there, and they're trying to mine, to take these blocks, pass them through the hashing function, get a random value, and they're trying to get it below what's called the target. The target is a number that all of the miners agree on, and it's like, you can figure it out based on what the previous blocks were. And the number is something like, let's say, well, so it's a certain number, and you need to, in order to produce a valid mined block, a valid hash of the block, it needs to be below that number. The number is called the target. If you can get below the target, then bam, you've mined a block. And the thing with the hash function is, like, given a blob of data and then the hash, I can hand that to anyone in the network and say, hey, look, I found this value. Like, I actually did mine this block. And the reason it's so difficult to do is that most of the hashes that are created are going to be much higher than the target, because it's just a random number. Like, what's the probability of rolling a die and getting, what's the probability of rolling 1,000-sided die and getting one 1,000,000 times in a row? Very, very unlucky, or very, like, you'd have to be extremely lucky to do it. Similarly, to roll this hashing function die and get these zeros, you need to be really lucky. So that target is set so that it gets mined roughly every 10 blocks. You can imagine if the hashing power increases substantially, the target will become a smaller number. It'll get harder to roll this die so that you get a number under the target, and it'll take longer to mine. And the system kind of self-corrects itself every 2016 blocks. It kind of looks back and goes, all right, how long did it take us to mine these blocks? Okay, we need to readjust. Here's the new target. Yep.
Alex, so I have a computer science background.
Okay.
Is there anyone in the crowd that already have a computer science knowledge? Yeah? How many? 1, 2, 3, 4, 5, 6, 7. Okay. So like maybe 50% of the crowd knows about computer stuff. So we know that if we do a SHA-256 on a constant, it's going to give us another constant.
Mm-hmm.
So from this formula, I can conclude that the block data is always static, and the miners, they always change the nouns.
Mm-hmm.
And the nouns now is like it's playing the die here.
Yeah, it's injecting a little bit of randomness into
so
it.
Like the miners are putting this formula inside a for loop.
Yes.
And they change always the nouns.
Yeah,
in order to one date and hope.
Yeah.
Of having a number less than the difficulty.
Yeah, that's a really good way to think about it. Think of just a for loop, and the for says like, or maybe a while loop. While hash is less than target.
Okay.
Update nonce. It's 1, it's 2, it's 3, it's 4, and compare the hashes. Just keep comparing. Okay. Yeah, that's like the basic mining construct right there. Yeah, thanks. And just to give you a scale of how much this is going on, back in like 2011, which was nothing, like there were no miners back then, the total Bitcoin network was more powerful than all of Google's servers running at the same time. Now, Bitcoin is just orders of magnitude more powerful than the most powerful supercomputer we have on the planet. It is the most powerful supercomputer. The problem is, oh no, we're gone. The problem is, it's doing the stupidest, simplest operation it can. Oh God, you'll never guess it.
What's the SHA-256 here?
It happens, guys. It happens.
Cool.
Sorry about that.
Yeah, just wiggle the mouse every so often. Cool. So this is a really important part of it, and this is a more technical talk, so maybe you want to, if someone feels like they just need like one question to really understand it, take a couple questions. Is there anyone who, is there anyone who has a question, something I said wasn't clear, something I want to clarify? Yeah?
So do you process the same data through the hash function until you get a good hash?
Yep, that's all a miner does. Or no, sorry, you don't. So, kind of. The problem is, so early on, yes. Early on, that's how it worked. The problem is this nonce is a 64-bit value, and these miners are working so amazingly, blindingly fast that they speed through the 64-bit space in like under a second. So the miners have been very clever in figuring out little pieces of data that they can tweak in order to inject some more randomness in and try to get a valid hash. Yeah.
And what is this data?
The block data? So yeah, a block is a collection of transactions. And I'll show you what the structure of transactions look like. But basically it's where am I taking money from and who am I Bitcoin from and who am I sending it to? So there's a couple fields in the transactions in the block that like aren't that important, and you can tweak them. Like there's a timestamp in the block, and you can tweak that. There's a little leeway in the Coinbase transaction, which pays the miner 12.5 Bitcoin. You can tweak that a little bit and get some randomness out of there. Yeah. Yep.
Do transactions ever get rejected just because there's too many transactions on the way, or do they get queued up and eventually the transaction will go through?
Yeah, so Bitcoin is really nice because it will like tell you immediately whether your transaction is invalid or valid. But let's say you have a valid transaction. That doesn't mean it's just going to get confirmed. You have a finite amount of space. Each block in Bitcoin is 1 megabyte. You can't put more than 1 megabyte worth of transactions in. A transaction is like roughly 500 bytes to 1,000 bytes, so it's roughly 1,000 to 2,000 transactions. But like right now, for instance, the backlog is huge. There's like, last time I checked, like 30 megabytes worth of transactions, which are just sitting there waiting to get confirmed, but they don't pay a high enough fee. So the miners don't want to include them. And that's why we have really high mining fees right now. Like I was trying to send my friend some Bitcoin, and I just was like, it's just too high. So yeah, long-winded answer, but yeah, they can be backed up. Cool.
Alex, I have a question. So how are the blocks linked to each other? So we have a block, but also it's a blockchain. So it should be a chain of blocks.
Yeah. Where's the blockchain name come from? So go way back to 2009. The first block was created. It's called the Genesis block, the birth block, the beginning block. And then when the second block was created, it included a pointer back to the block behind it. And that pointer, pointing back to the first block, is like an immutable part of that second block. And then the third one, same thing. Third one, same thing.
So I guess like a linked list architecture, right?
Yep.
Structure.
Oh, and you can build a pointer from the previous one to the new one, so it's kind of like a doubly linked list. Yeah. But yeah, super basic data structure, linked list. Okay, can you scoop it forward? Cool. Okay, so one more thing about mining. There are just giant farms, server farms, warehouses, a lot of them in China, really where the electricity is the least costly, is a really good place to set up these mining rigs, to set up these mining farms. So if you go ahead one more, yep. Maybe you can see it. There are just racks and racks of these miners, but at the same time, You can't see it too well, but it's in the bottom left corner. The miners, like, you can hold in your hand. Some of them are like yay big. So you can mine just in your home, like under your bed or in your closet as well. The more miners you have, the more dice you're rolling, the more likely it is that you'll find a block.
Are they the same miners that are used on like, scalable, like the industrial guys that are doing it, and the guy at home, it's the same equipment?
Yeah, yeah. The Antminer S9, I might be a little bit behind, but like at one point that was the piece of mining equipment you use. And yeah, yep, the little guys and the big guys. The big difference was the big guys have way more, they're cooled, they're maintained by a workforce of like 100 plus people. But yeah, the idea is the same, you're just rolling that die.
Do each GPU roll a random die, or they work together like to find this the hash tree? Like,
Yeah.
Can you connect all the GPU together to find the hash string faster, or all GPU is just like a random die?
It's all random, yeah. So like basically the way you would get them to work together is that you want to make sure that none of them use the same nonce, right? That same number, because then you're just doing duplicate work. If this miner chooses a nonce of 42 and then this miner does as well, they're both going to get the same value.
This is what I was asking, if it was
Yeah. Yep.
Please.
Yeah.
But you said the nonce number is a random number. It's not constant.
Yeah, it's not. It doesn't have to be random. You can just like set it at 0 and increment it and keep incrementing it. Yeah. The purpose of it is just, remember how I said you change one bit and the output hash changes totally? You just need to change one little bit of information, and that's the nonce. Yep.
Talking about the GPU versus CPU. So
Yeah.
as CPU, we have a multi-core CPU, right? So we have a quad core, we have the i7.
Yeah.
And with an, let's say an i7, so we have 8 cores in the CPU. So these 8 cores, they can act like
Yeah.
8 multi-threading miners, right? So it will be faster. But GPUs, they can perform like thousands of multitasking together. So that's why today GPUs are very promoted as being good items for.
Yeah, you can think of like the purpose of a GPU is to print pixels on your screen, and you have like thousands of pixels on your screen. Each of those operations is kind of like rolling the die or computing the hash function. The thing is now, so back in like the first 2 years, you could just whip open your laptop and start mining Bitcoin, and you'd get 50 Bitcoin every 10 minutes. Then it started to get harder. Then people realized, oh, I can use GPUs because they're doing this really simple algorithm, but they're 10 times, 100 times faster. Nowadays, people have, like, a GPU is actually like really general in what it can do. It can display games, like all different types of games, and it can run physics simulations, whatever. The miners that are running now, they have one purpose. They do nothing but mine Bitcoin. And they've gone in there in like the fabrication, like basically computer creators, and they've like made sure every wiring is so efficiently organized to mine Bitcoin. It can't do anything else. It's like the stupidest computer, and computers are already really stupid. It's the stupidest computer you've ever seen. Because all it can do is do SHA-256 twice on this amount of data. And that's why you can't run on your computer anymore, is they're so fast. Okay, so I explained you've got some coin because someone sent it to you, a miner at one point created it and then sent it to you. And now you want to send to someone. How do you send to someone? You need their address. So their address is, you can think of it kind of like an email address. It's just like a destination. It's a point in the system. But these addresses look like very ugly. They're long, random strings of numbers that either start with a 1 or a 3. And the 1 and the 3 are for the different versions of addresses you have. And based on what version you have, you can do different things with it. So a 1 version, the one that starts with a 1, is just like plain old address. We say you need 1 key to spend it. A 3 is for what's called a multi-sig address, and it's where people send funds to the wallet, but then I need, let's say, 2 people to sign off on it before we can spend the funds. So it's like kind of like having a joint account in a bank. You need multiple people to sign off, which is good because now multiple people need to get hacked before the coins can get stolen. So it's a way to protect your coin.
Alex.
Yeah.
So the number 1 is one address, right?
Yeah.
And number 3 is multiple address. But like I see their size, right? So
Yeah.
it looks similar in size. So how can you store multiple address in the second one and it looks like the same size of the
Yeah.
first one?
So we can do that because these what you're seeing right here are actually hashes of the original addresses. So going back, the thing with a cryptographic hash function is that you can take a little data, a lot of data, unbound, whatever, huge amount of data, and it will hash down to a fixed size. So this string of numbers and letters is actually a hash of the original addresses, or sorry, keys, which themselves are actually a computer program. And this is like one of the deeper concepts. I hope we get to it at the end, but we'll see how we go. If anyone's interested in Bitcoin script, like come talk to me afterwards. I'd love to explain it, but I think it requires more time than we have now. So for right now, just think it's about the keys that you have. So what are keys? Bitcoin, like one of the fundamental components, is this idea of a public-private key cryptography. You have 2 keys, a public key and a private key. The public key you give to everyone. That's how you create your address. Your private key you keep secret. And you make sure that no one ever knows your private key. Because if someone knows your private key, they can steal all your coin. Yeah?
So to make sure no one knows your private key, you never put it on your computer?
Exactly. Well, you always password protect it. And if you have a large amount of funds, then yeah, you never put it on your computer.
Because there's malware that can read it.
Yeah, because because there's malware. You don't know what malware is happening. You really need to be very secure about these. And so the best thing is really what's called a hardware wallet. And it's like a little USB stick that you can store in a bank. And there's no way to take the private key out without totally destroying the device. So folks who, if you have I'd say more than 10 Bitcoin, you should use this.
What about paper?
Yeah, so in the end, I was saying public and private keys. All you need to spend and to show ownership of some coin is to have a private key. And the private key, I'm not sure if you can see it, but that bottom value that starts with XPRV, XPRIV, right here, if you write that down on a piece of paper, that's what you need to store your coin. So it's kind of, I don't know, I think it's kind of interesting. You can have a piece of paper that's worth millions of dollars, a little scrap of paper, because it has a private key written down on it. And I'll explain how that private key works. Yep. You go forward.
Where do you get
Yeah.
that private key number from?
Yeah, so it's pretty much a random number. And then you use that random number along with what's called an elliptic curve to generate the public key. And the public key is the thing you show to everyone. But the private key is, it's just a random number.
Where does it come from? Does it show up on your computer or?
Yeah, you press a button and you say generate a key for me, and then some functions run in the background which generate a really large number, like a pseudo random number generator. You use one of those.
So as soon as it
No, or once you generate it, it's there on your computer. Hacking just really means, can someone who's not you view it?
So if I can't put my private key on my computer for fear of it being insecure,
Yeah.
how do I spend all my money? So I just made $20 million.
You use one of these hardware tokens, and they have like a secure interface between the token and the computer. And the computer may have the functions which like assemble all of the necessary data. But then your hardware token is the one that actually signs it, the one that actually attests and says, I, Alex Melville, send these funds to Jonathan.
So your computer never actually sees any of the data.
Yep, yeah. There's like an impermeable layer between the two. Okay. So talking about like what is this attestation? Like I said, you have a public-private key. The basic idea is it's like a regular signature. Okay, like when you sign a check, you say, I indeed send these funds to whomever, except it's digital. And it's using math provable to see that the person who you think really signed it. So keep going. And it looks like this. It's just, go back a little bit. It's just some random looking data. That's what a signature looks like. But you can use the public key to verify that the correct person did sign it. And that's how Bitcoin uses these. So under the hood, they're using this type of math called elliptic curves. It's just a type of curve with a particular function that has interesting properties. And around like 50 years ago, some really smart people discovered, whoa, we can use these elliptic curves to create cryptographic algorithms. Like we've been studying these since like the Roman times, but only now have we discovered, or recently in the modern times have we discovered, whoa, we can write extremely secure cryptographic protocols with them. So, and it just involves taking a point and like moving it around on this curve and bringing it to a particular other point, and you have your public key and your private key, and they're just points on this curve. So I just want to show you like higher level how this works. So can you skip through this? Yeah. So imagine you want to pay rent, and you send over a message saying, I want to pay some rent to Bob. Bob goes, cool, okay. The problem with regular signatures is that you can send them over. Someone in the middle can intercept it, change it with one of their own, like forge a signature, and then send it back, and Bob wouldn't know any different. So with public-private keys, you sign a message with your private key, just like you're signing a transaction. You sign a message with your private key, and you give your public key to Bob. Maybe you meet in person beforehand. So now, keep going. You sign it, the message with your private key, hand it over to Bob. Bob can then take the message, the signature, and the public key, combine those all together and go, cool. Alice really did sign the transaction, really did sign the message. And he can prove this with math, pretty much, these cryptographic algorithms. And the fancy thing is if an interceptor comes in and tries to change the message, change the signature, Bob can know what happened. So this is what's used in Bitcoin when, imagine that like I could just go and steal your funds by pretending to broadcast a transaction from you. It'd never work. The way I need to do it is I need your private key, but you need to keep that protected. Okay? Okay, so we're sending. I just want to show you what the structure of a transaction looks like. Keep going. Go back. Oh, yeah. So a transaction just has inputs and outputs. Where is the money coming from? That's my money. It has the signatures. And then where is the money going? Who am I sending from? Just has the addresses and the amounts. Keep going. And the thing with inputs is that they're just references to other transactions that have come in the past. So it creates kind of this other chain. Instead of a blockchain, it's a transaction chain of transactions in the past. And outputs are really simple, just an address and an amount.
Okay, so let's say that you're sending me a transaction.
Yeah.
So what will be the input and the output of this transaction?
Yeah. So let's say that a miner sent me 50 Bitcoin.
Okay.
And that's like, I have my 50 Bitcoin, and I want to send it to you.
Okay.
My transaction would have one input that points to the transaction where that miner generated it out of thin air, right? The miners are generating it out of thin air. That's the input. And then the output is just your address, which you handed me. Maybe it's one of those one addresses.
Okay, but in this case,
and 50.
What's going to happen if you receive 50 Bitcoin from the miner
Yep.
and you want to send me only 1 Bitcoin?
Yeah. Okay. So where does that 49 other Bitcoin go? Yeah. So the way Bitcoin works is it's kind of like having a bunch of change in your pocket. And you go and give like a penny and a dime and a toonie to someone, but you want change, right? You want some like, that doesn't always add up to the full amount you want to send. So you want some money back. So you actually create a second output back to yourself, back to an address you control, which you have the private key for 49 Bitcoin. So 1 Bitcoin to you, 49 back to me. And these outputs are just, there's pretty much change addresses on every transaction because you always want some money back. You never want, it's really unlikely that you would send the full amount. Yeah?
Yeah. Is it possible to send a 0 transaction just to confirm the channel?
Yeah. Yep. And those have a special, usually they're what are called op returns, and like they're provably unspendable. And this is like another thing where you can add arbitrary data onto the blockchain, sort of like where you carve your name into the tree trunk. You can write a message in these transactions. But yeah, it's valid to send a zero transaction output.
Okay, so we demonstrated that we can send a transaction with 1 input with 2 outputs, because the first one it is paying me 1 Bitcoin, and the second one is paying back yourself 49 Bitcoin.
Yeah.
Can we revert it? Can we have like 2 input, let's say you and David paying me 2 Bitcoin? Like
Yeah.
1 Bitcoin, and a single output, which is only me?
Yeah. Well, so let's say just over time, these outputs have gotten smaller and smaller, and I want to send you 10, but I only have like a 2, a 3, and a 5. I take those, I create a pointer, 3 pointers to each of those transactions, sign each of them, sign the inputs with my private key, and then 1 output to you, and then maybe a change to me as well. So yeah, there's any number of inputs, any number of outputs you want. Yep. Okay, we're almost done. I just want to show you how these transactions are actually broadcasted. It's called a gossip protocol, and it's exactly what it sounds like. So you're a node sitting there, and you want to send to someone else. I send it to Ramsey. He gets a transaction, and then he tells everyone he's connected to, look what I got, look what I got, look what I got. They do the same thing. So can you go back a couple slides here? Go back. Yeah. So starting, like, let's say this is the node, and you want to broadcast it. Keep going. It'll jump to every node that it's connected to, and then it'll jump and finally fill out the network. So it's a really like message-heavy way, but very fast way of communicating a transaction. And like on average, you see transactions getting broadcasted across the world in like 10 to 30 seconds, depending on the speed of the various networks. But it's very fast.
Alex.
Yep.
Let's say that Osama bin Laden was here.
Okay.
And he decided to take his wallet and to lie about what he have received from someone. And he would lie to everyone. He say, okay, look, I have 100 Bitcoin, 100 Bitcoin, 100 Bitcoin, 100 Bitcoin.
Yeah.
How would the network or the people know that there is an Osama bin Laden here trying to hijack the system or trying to steal money?
Yeah. So they would never know it was Osama. Well, very unlikely. But they would very easily, because they're running full nodes, be able to know, hey, this input, what you're specifying, that's already been spent. Because all of the full nodes keep like a kind of a running tally of what outputs are spendable. They're called unspent transaction outputs, UTXOs. And every time a transaction gets spent, you can imagine these as just like a pool of unspents, kind of like a pool of coins. And anytime a transaction is spent, you delete one of these, well, let's say you use one input. You delete one of these unspent transaction outputs from the pool because you spent it. And then you create a new one for each of the outputs you have in your transaction. So you may actually be increasing the number of UTXOs, you may be decreasing it. It all depends on how many inputs and outputs you have. But if you don't have an unspent transaction output that you're trying to spend, immediately the nodes will know, bad actor, and they'll actually just ban you. They like won't accept connections from you anymore because you've been bad. So, yeah.
It's like every node also have its own reputation.
Yeah. But it's like if you screw me over once, you're gone. Yeah. Okay, so cool. We've got our block. We've broadcasted it to the network. The miners have included it and mined it. They've rolled their die. One of them found it, said, "Hey, look, everyone," and your transaction is in there. And now your transaction is in the blockchain forever until the end of time. Okay? Keep going. And so that's the full life of a transaction. Thank you. So yeah, I got some questions from folk after about how mining works. I think that's really confusing, so maybe there's some more questions about it, but hope that made some things clear for you.
Yeah, where does the target come from?
The target is just derived from, so in the beginning, there was some target.
How it adjusts to get the mining to one transaction block every 10 minutes? Who decides the target?
Right. The target is just derived from the previous 2016 blocks. So go back to the very beginning. The target was, let's say, some really high number. Some amount was mined, right? Some hash power. And then you look back and you go, on average, did we take longer than 10 minutes or less than 10 minutes? If it's longer than 10 minutes, then that means that the target was not hard enough. So the target will get lower. It'll get harder to mine. And the algorithm for that, I don't know it off the top of my head, but you can imagine it as just a function of how long did it take on average, and what's the current hash rate? How many hashes are being done on average thus far? But it's something that's easily derivable from nodes on the network.
Yeah, who is doing this job of, okay, now the target will be this high?
Yeah.
Is it?
Everyone is doing it on their own, but they all come to the same number. It's sort of like a hash function where even if you have a bunch of different people, if you give them the same data and the same hash function, they'll get the same output. It's deterministic from the very beginning of the system. But the actual function, it's really just about setting that interval so that it's roughly 10 minutes every time.
So every node is doing the computation of the next target?
Yeah.
And they all come to the same result?
Yep.
And that's the next target?
Yep.
David?
Yeah, so a full node helps to secure the network.
Sort of. In the following way. If the network was filled with all bad actors, all bad nodes, then you could be lied to at any point. Right? Like the node would say, no, actually, this UTXO hasn't been spent. But as long as you have one honest node, they can tell you the truth, and they can prove to you, oh, this is actually the state of the world. So they aren't securing the network like the miners are. They're not making new blocks, but they're protecting you from being lied to. But there is no like incentive to run a node, unless you're just a hobbyist. But like our company runs them because we need them to validate the network.
Yes, observer?
In terms of the Ghost protocol, how does it broadcast? Like what data structure is that? Is that just like a random tree that's expanding?
Yeah. So it's a gossip protocol, not ghost. Gossip, like you tell everyone as soon as you can. And there's not really a data structure. It's just like on average, I think you're connected to 8 nodes. And there's some message buffer that you put the transaction in and then push it onto the wire.
Okay,
But
so emitting.
yep, you're just emitting, and then I think you keep like a cache of what transactions have I seen, so that you just don't keep broadcasting the same one over and over. Yeah.
Yeah, one of the main sales point of Bitcoin was that all transactions were anonymous.
Yeah.
So you just said, you previously said that every transaction is registered on the blockchain. But who have access to those transactions and where does it came from?
Yeah, so anyone can read them.
Okay.
It's a public ledger, is another phrase for the blockchain.
So how is it anonymous if anyone can read it?
Yeah, so it's not actually anonymous. It's like pseudo-anonymous is what they call it. And the idea there is that it's anonymous in the sense that all you see when you read a transaction is one of those long random addresses is sending to another random address. But the thing is, if like right now, let's say afterwards I buy some Bitcoin from you, or actually no, rather I sell you some Bitcoin, so you give me your address, suddenly I know that this address is connected to this person I met in the real world. So that's like a big loss to privacy, because then I can kind of follow through the chain and see where you're sending. So it's pseudo-anonymous. Pseudo being that you do know they're big, long, random numbers, but you still know what they're sending. And there are coins out there that are truly anonymous, like cryptographically proven, to show that you don't know who's sending, you don't know who's receiving, and you don't know how much they're sending. It's crypto magic.
It's basically, since I buy my coin on Coinbase, which is directly related to my bank account,
Yeah.
I'm no longer anonymous, and my bank can know what transaction I did.
Yeah, Coinbase would know, and then your bank would just contact Coinbase.
And doesn't it, how do you say, scramble the lead if I go on an exchange and start trading with multiple wallets?
Yeah.
I'm wondering what you're trying to do.
I'm just wondering, because I mean, one of the main sales points was that it was anonymous. So I'm just wondering, if it's not that anonymous.
Yeah.
What's the point?
It's not that anonymous. It's not anonymous if you use these systems where you attach like your real identity to, right? But even with the really truly private coins, that would still be a problem, because they know like, oh, this person wants to receive, however many Monero or whatever the privacy coin you're using is. But if you don't use the exchanges, if you want to go like full crypto, like the exchanges are just sort of a crutch right now, that we need to take the old world money and move it to the new world, right? So if you're that crazy, then you just see it as a temporary evil. And it'll get better if you only trade in crypto.
You know?
Yeah, you mentioned earlier that there was a limit for the amount of Bitcoin, right?
Yeah.
And you also mentioned that that might change, and they're thinking of changing it or modifying that. So who are they? Like, because you mentioned also you compared it with Facebook, that it's global, but it's not decentralized. terms of they have servers somewhere and then Facebook controls the server.
Right.
So who controls what direction is Bitcoin going?
Yeah.
How is it decentralized if there's someone making a decision that they're gonna increase the limit or?
Yeah, really, really good question. So we're still trying to figure out what is the best model here. It's like, how do you govern a collection of people who you don't know and no one is supposed to be the leader? The main people who determine how the software is used are the users. Like if Bitcoin didn't have any users, then it wouldn't matter who the developers or the miners are or the businesses, because no one would use it. So, but it's also about the developers, because the developers are the ones who actually go and like make the change and make it be 2 megabytes instead of 1 megabyte, or 42 million Bitcoin instead of 21 million. And then the miners also influence it, because if the miners don't want to secure the network, then you won't have any mining power. You won't have a secure network. They'll move to another coin. So that's why I said, I think what I was talking about was that it's 21 million now, and it's possible to change it through something called a hard fork, where you do like a non-backwards compatible change to the software, and there's a permanent split in the chain. A new coin is created. But to do it is so difficult politically that I don't think it would ever happen unless something like really big changed about it. Unless there was a really big problem with 21 million Bitcoin.
Jonathan?
So you're saying is the software is open source and anyone could change it, then what matters is just do a bunch of people decide to go along and be like, yeah, I guess that's where our money is now?
Yeah, this is where the voluntary nature of it is. It's like, if you want to buy into this system, you're good. But if you start to disagree with it, fork it. Go to another coin. Make a new coin. It's really easy to make a Bitcoin. You just download the software. You can go and change the name from Bitcoin to AlexCoin. And then let's start mining it. You know? But who would ever use that? Because who wants AlexCoin? You need like some new kind of new technology that your coin adds, or this is what these ICOs are trying to do. They're trying to add some kind of new take on what a cryptocurrency can do. So yeah, you need buy-in from a lot of different members in the community to make it work.
Do you mine it yourself?
No, not anymore.
So what's the biggest hurdle to doing it?
For me, it's that I don't live in one place long enough to set up a mining rig and get it working.
But you already said mining is no longer profitable on an individual basis.
Oh, sorry, I was wrong when I said that. It's definitely profitable on an individual basis, but not for Bitcoin. There are a bunch of other cryptocurrencies that use different hash functions that the ASICs, the computers that made it non-profitable for me to mine, are totally useless for. So those coins, yeah, you can still mine those even on your computer. Yeah, like last year I was mining a little bit of Zcash on my computer. On actually my computer they gave to my brother. But yeah, I'm not mining it anymore.
So why is Bitcoin not profitable for you now as an individual?
Because like the number of hashes that I could do on my computer, let's say I had it running my entire life, is equal to what one of these ant miners can do in like less than a day. And so the odds are so stacked against me that it's possible, but it's so unbelievably unlikely that it would be like winning the lottery and simultaneously being struck by lightning. And yeah, that actually that's like incredibly likely compared to me finding Bitcoin.
So essentially, if someone just got an S9 and miner, they would be as efficient as anybody else. It's neither right, but it's an individual.
Yeah, but they need a lot of them. A lot of them. Because each new miner you add is another person rolling the dice there. And the moment one of them, it's kind of like, you remember from the Willy Wonka and the Chocolate Factory. Remember that one person who her dad hired everyone to open the candy bars? And the moment one of them found it, yay, we got in. It's kind of like that. You can have one little person opening the chocolate bars, but it's really unlikely.
Oh, so when you have like an S9 or something, whatever, you have like a whole bunch of them working on the same problem at the same time.
Yeah. Yep.
Is there an optimal number?
Nope. The more the merrier.
With just whatever.
Yep. Yep.
So the point we're getting towards is that Bitcoin is gradually getting centralized in some areas like mining.
Yeah. Yeah, they call it an oligarchy. Because if you wanted to, there's like 5 or 6 people who control more than 51% of all of the mining power. And 51% is a special number because once you control over half of the mining power, like the whole system really breaks down and the cryptographic guarantees don't matter anymore.
Can you talk more about that?
Yeah, sure. So it's called the 51% attack. And the whole idea is that you have a bunch of these miners all around the world, and they're all like, they have the same versions of the blockchain, more or less, and they're each trying to add the new block. And if you have, normally you have like many little people who are mining, one person finds it, broadcasts it, everyone else updates their view, keeps mining. And let's say, someone finds it here, and they broadcast it, but this guy goes, no, I'm going to mine my own, I'm going to keep mine my own chain where I try to do a double spend attack. That's why you would do this sort of attack. Now they have a big problem. They're one block behind. So they need to find a block all on their own that equals the height of the block that was just found, plus another block in order to have everyone else start mining on their chain. Right? They're one behind. They're going to constantly keep falling behind unless they control over half of the power. Because then they're behind, right? And let's say they have let's say that they have over half. 50% chance this guy goes ahead and this guy stays where he is. But also 50% chance that this person finds it. Once you have that weighted a little bit in your favor, given enough time, you're going to catch up. And you're going to actually surpass the other people. When I say when I have these two fists, one represents the minority, the honest people in the network that have less than 50%. And then there's this central malicious miner who can outpace everyone else because he has so much mining power.
The rule is that the longest chain wins?
Exactly. The longest chain wins. Well, really it's the chain with the most work, but that's almost always the longest chain. Yeah. So centralization is really bad because the whole point of Bitcoin is to be decentralized and not have anyone control it. But one big worry people have is a lot of the miners are in China, and now with the Chinese government saying they're going to shut down Bitcoin, I guess China controls Bitcoin, maybe? I don't know. That's up for interpretation, and we'll actually see how it pans out. Maybe it won't be that bad. Maybe it will be really bad. Maybe this is the death of Bitcoin. But yeah, centralization is bad, particularly for mining.
These specialized ASICs miners earlier, can you build ones for other cryptocurrencies as well?
It depends on the hashing function, and what it really depends on is how simple it is. So Litecoin is kind of special because their hashing function is really complex. And it's meant to be, they call it ASIC resistant, because it's too complex to go and individually wire everything to be really efficient. And it just has to do with the physics and computational structure of these algorithms. But it is possible.
Two more questions. Louis? Yeah. Why is the threshold 10 minutes? Why do you always want to fix the target to be 10 minutes? Why not 1 minute, 1,000 minutes?
Yeah, it was chosen by Satoshi. Yeah. So there is some limit in that if the frequency is too small, so let's say the frequency was every 2 seconds, well, it takes longer than 2 seconds to propagate a block around the world. So if you had blocks like coming out every 2 seconds, then you would be constantly falling behind and the network would be mayhem. But 10 minutes is normally always enough to broadcast it around the world. But yeah, it could have been 5 minutes. 5 minutes, given the speeds of various networks around the world, that would have been enough. But it was 10. Yeah.
And if it wants to, like, the developers all agree to change that to 5 minutes, who does the change of the code? Like, the question was just asked, but right now, at this moment, who takes the lead on these decisions and like, how are they actually implemented?
Yeah. So a good case study is about this time last year. I would have, if you had asked me that, I would have said Bitcoin Core. Bitcoin Core are these collection of 500 roughly developers, maybe 10 of which are like really well known and really influential, like have a lot of clout in the project, have a lot of high reputation. But in August, there was the first like real what's called hard fork, where there was a split that cannot be brought back together, and that's what formed Bitcoin Cash. And then there was a new set of developers. So these forks have kept happening. So really it's whoever is the most prominent developer for the coin. Like if you and I decided we wanted to go and bring it down to 5 minutes, then we would go and create Montréal coin and it would have 5 minutes. And maybe we'd be the only miners, but yeah, it would be us deciding. People would kind of lean on us to do it.
One more question. Awesome. Very good.
Yeah, I think we're all tired, so thanks for coming. Thanks for staying with me this long.
Thank you, Alex.
Whew, thank you.
Awesome.
Yeah, good questions. Feel like a blockchain developer now?
Yeah, it does.
You get to use that mastering Bitcoin?
Tomorrow you're leaving, right?
Friday.
Friday, okay.
Yeah.
Are you planning to do something during these 2 days? Farewell goodbye party, maybe?
Yeah, I've been planning all this, so I have no plan. I have no real plans.
Awesome.
Yeah.
So let's do something before you leave. What
Yeah.
time do you leave Friday?
Just like actually before work, like 4. So Friday.
So
Friday's no
Thursday
good.
night, maybe.
So tomorrow's the night.
Yeah, tomorrow is the night. Because
Yeah.
I'm going to organize it.
Okay.
And
I would love that, man.
Awesome.
Yeah.
Great, man. Thank you so much.
Okay. Yeah. Yeah, that was fun.
Thank you, sir.
Yeah.
That's cool, man.
Yeah.
Good.
Yeah, thank you for this.
Thanks.